Okay, so we have a 3-mass pulley system on an inclined plane that is friction-free. So this is a friction-free problem. The first thing that we're going to look at is our masses. We have them listed out here. We're going to look for our net force, which is going to be in the same direction as our acceleration. Remember that objects always accelerate in the direction of the net force. We're going to look at two tensions because we have a string here and a string here. Remember, those are also massless. They don't count. This is a friction-free pulley, friction-free surface. So the first thing that we want to do is label all the forces acting on the system and then pick a direction that the system will move. So I am going to go ahead and label my weights. This is M3G, right? It's this mass times the acceleration due to gravity on Earth, which we are saying for this problem is 10. So this is going to be 30. This weight right here is M2G, which is going to be 60. This is going to be M1G, which is going to be 40. Notice that this is in line up and down. So I don't have to break this down into any components, but this is at an angle to this surface. This is at an angle to this surface. So I'm going to have to break both of these down into my X and Y components. And I'm calling my Y component my F perpendicular. I'm calling my X component F parallel. So I'm going to connect this around. Do this. Okay. And I don't have to break this one up. So this right here is my F perpendicular because it forms a right angle to this. Going up against this is actually my normal force. These should be balanced because it's not sinking into the surface and it's not bouncing off the surface or levitating off the surface. So these should be balanced. This is also a perpendicular force here, forms a right angle to this surface. F parallel. Coming up then is my F normal. These again are balanced out for this mass because it's not sinking into the inclined plane, it's not lifting, or this force, the perpendicular force, the normal force is not pulling it up. Perpendicular force is not pulling it down. So I'm not really worried about those two forces, but I do want to notice and pay attention to my F parallel of both of them. So I'm going to put my F parallel up here and say F parallel is really equal to M1G sine theta, because this angle right here is the same as this angle here. And I've shown you mathematically how that is. This forms a 90-degree angle. 90 plus 25 plus some number has to add up, because this is a little triangle, has to add up to 180. Put that value there. This perpendicular force is also 90 degrees to that angle. So I take this number that I just figured out, and I take 90. If I add those up, subtract from 180, I should get 25. Same thing here. If I were to make this a large triangle, pull this all the way down, this is a bigger triangle of this. So this too, I'm just going to highlight it red, that these are all the same. These are all 25. So that's why it's, when I say theta for this and this, it's both 25. If I look at the way that everything is set up, I can see that this side, the F parallel, is opposite this angle. That perpendicular is adjacent. This is the hypotenuse. Again, this is hypotenuse. This is opposite. That's the adjacent side. I'm not worried about the perpendicular force because I can use my weight always. If I know my weight, I can use that plus theta, if I'm given that, to find the F parallel. You always use your unknown in that problem solving, right? If you don't use your unknown, you're not going to find what it is in this situation. So that's why this is sine theta. So I'm going to do, so this is our F parallel. Now I've got tension in this rope going against that mass. So I'm going to label that as T1. I have tension going down the rope the other way. T1, they are the same. Now I also have this F parallel is up here, so this gets a little tight with space, but I'm going to put my F parallel here. And this is M2G sine theta. Okay, this tension here is T2, going up here is T2, they're the same. That's my only other tension, and then my weight. So I'm going to define which way I think it's going to go. So I am going to, it doesn't matter which side we pick, but I'm going to go this direction, and I'm going to say this direction is positive. Really important that you're very clear when you create this directionality and not just slop you with it so you can't see your own handwriting. So you need to make sure that you know that this is up and up is positive. So you just carry it, follow it along. So when we're doing this problem, we're trying to figure out our net force. We're following that line that we created there. So basically, we're looking at everything that's in line here with this addition, right? Because this is really in line with that. So we're taking our F parallel for M2, our F parallel for M1, our weight for M3, and we're looking at these tensions on the rope. So I'm going to set up my F net equals MA, the second law of motion. And I'm going to, it doesn't matter which side I start from, so I'm going to start from this side and move around. This is in the positive direction, so this is really, my F net starts with positive F parallel, right, for here, minus T1 plus T1, because this is the same direction as that. This is a plus F parallel, and I should label this as mass 1. That's our second F parallel, right? We have our T2 is going against that direction, so minus T2. Look at this T2 over here, so I'm following it along. This is up, positive. And then this is M3G, but it's going against our positive, so it's minus M3G equals our mass. Our mass is of the entire system. The entire system is going to accelerate at the same rate. So we have 4 plus 6 is 10 plus 3 is 13 times the acceleration. Notice that my tensions cancel out. So I'm going to just put in what this number is. So I'm just going to, in my calculator, do M1G sine theta. So I'm taking 4 kilograms times 10, acceleration due to gravity, times sine of 25. I should get for this one, it's going to be positive 16.9 newtons. This F parallel here for mass 2 is pulling this direction. So I'm going to take my second mass of 6 kilograms. So 6 kilograms times 10 times sine of 25. And for that one, for that F parallel, I should get 25.4. So So I've taken care of that one. And then this mass over here times acceleration due to gravity, so that should be 30, but it's minus 30. It's equal to 13 kilograms times A. So let me go ahead and do some quick math. So we have 16.9 plus 25.4 minus 30. So I calculated that to be a positive 12.3 newtons. It's equal to 13 kilograms times the acceleration. So we're going to take this out to get acceleration by itself. Remember that Newton is really kilogram times meter per second squared. So we divide this by 13. The acceleration of the system. You could sort of tell that this was going to sort of balance out a little bit. This sum is greater than this number. Remember that if your F parallel force, total F parallel force, is greater than this weight that's hanging off, it'll move down. If your F parallel, the sum of your F parallel in this case, is less than the weight, it will go up and over. And if this F parallel happened to equal this weight over here, these two masses, their F parallels equal this weight, then it would stay still, even on the frictionless plane. So we have our acceleration is equal to 0.9462 meters per second squared. Again, I'm not sig figging in these problems. I'm just carrying basically however many numbers I want to. But remember that when you are sig figging, you're going back to your original value. So we would sig fig down to 1, but we can carry some numbers through. So for F net, this number was really a positive 12.3 newtons. So we figured that one out. And this is a positive 0.9462 meters per second squared. So we did this one and this one. Now we need to find our tensions. So we're going to break our T1 down box by box. So I'm going to choose my bookends. So I need to make sure when I circle this, I'm circling all the forces acting on it. Same thing here, and that's going to be the one I'm going to use for T2. So for T1, I'm going to say F net equals MA. So I'm looking at this box. So this is, again, my F parallel, which I know on this side is a positive 16.9. I'm looking at this line right here. So I'm going to say positive 16.9 newtons minus this tension because it's going opposite what I chose as my positive. So minus T equals, and remember that these cancel out, and they're not affecting this line of motion, so I'm not worried about those. Remember that your weight has already been broken down into components, so it doesn't really exist as it is drawn anymore. I mean, it does, but we've already broken it down, so we don't use it twice, right? So we're just using this component of the weight. Is equal to our mass 1, which is 4. So this is 4 kilograms times the acceleration of the system, which we already calculated, 0.9462 meters per second squared. So I'm going to say, let me clean that number up a little bit. So we have positive 16.9 newtons minus T equals, I have positive 3.785 newtons. We're going to subtract that out to get T by itself. So we have negative T equals negative 13.12, which is really, right, the negative and negative cancel. So really it's positive T equals positive 13.2 or 12. That's for T1. For T2, same process. We're focusing on a different box. This tension is the same as this tension here. I just chose this box because I don't have to deal with sign anymore. It's fine. We've already calculated it, so it doesn't matter. You should get the same number. So we're going to say our M3G, which is 30, is negative because this is the same positive as up, so keep in mind that. So that plus T2, right? Because T2 is up. This says up is positive. I'm focusing only on this mass, so it's 3 kilograms times the same acceleration because it's accelerating with the system. So that's going to be 0.9462 meters per second squared. So let's take that, clean that number up a little bit. So that's going to be equal to 2.8386 newtons plus T2, and then this is a minus 30N, plus 30, plus 30. So we have T2 equals 32.8386 newtons. And this is positive. Remember that tension can't be negative, because if you show it as negative, you're saying that it's actually pulling something down. Tension actually pulls something up, doesn't push it down. So a rope or string can't cause the motion of the object. It can hold or help to hold the motion in, or the object in place. I'm going to go ahead and put my that's T1. So I'm going to put my T1 here. This is positive 13.12. This is positive 32 point, I'm just going to round it here. Again, if I were sig figging, I'd need to go back to the original numbers, and that's going to leave it both at just 1 sig fig if you're sig figging. All right.